In this section, we are going to keep going in Chapter 6 and look at some more functions and their inverses. And here we're going to look at inverse trig functions. So let's get started. So we're going to spend some time talking about the inverse sine function. And the idea here is that if you take sine, whose domain is normally negative infinity to infinity, and you restrict it to a smaller domain, then it becomes a one-to-one function. And whenever a function is one-to-one, it has an inverse. And so we just call that inverse the inverse sine function or the arcsine function. And so arcsine, it can be written as arcsine or sine to the -1 power. Its domain and range are just the domain and range of sine switched. So its domain is -1 to 1, its range is negative pi over 2 to pi over 2. And you can see from the previous slide, that's the opposite. So the domain and range just switches, because it turns all the x's into y's and all the y's into x's when you do an inverse. So we need to talk a little bit about trigonometry. So this is just a quick review of stuff you've seen before, but I'm going to lay out what I expect you guys to be able to do on a test. Make sure you're practicing the techniques. If you're just Googling all the answers, then you're not going to get points on the exam, because you have to show work. The work that I'm showing in the examples is the same amount of work you need to show. So here we have just the lay of the land, right? So x equals sine y takes an angle y as an input and returns a ratio x equals a over c as an output. Right, and that's what we do with sine. So this doesn't have to be the unit circle. This is important. It's allowed to be a unit circle. If you want to divide everything by c, then it becomes the unit circle. That's fine. You just don't have to. So when we have the arcsine, y equals arcsine of x, it takes that ratio as the input, a divided by c, and returns an angle y as an output. And of course, a, b, and c are related with the Pythagorean theorem. So you will always be given 2 of the 3 sides, right? You have to be. Because to do the arcsine, or arctangent, or arccosine, you need 2 of the 3 sides. All right, so let's jump in and do a couple of these. And the techniques I'm using here are the same techniques you're going to have to use on a test. So let's look at the first one, arcsine of 1/2. So essentially what you do is you just use what we said on the previous slide, and you say arcsine of 1/2. So that means sine of some angle gives me 1/2. Just switch x and y. So sine of what angle gives you 1/2? Well, it's pi over 6. Do not list an angle that is not in the domain. Okay, that will be marked wrong. So if you're just looking stuff up online and it says pi over 6 and negative pi over 6 is not in the domain. So you have to know the domains of these functions. They're listed later on, but at least for now, you have to know the domain of arcsine. All right, let's look at the next one. So that's the answer, pi over 6. Tangent of arcsine of 1/3. So what you might be tempted to do is type it into your calculator. You might be tempted to do that. And you're going to get some funny decimal. The homework will not accept a funny decimal. I will not accept a funny decimal on an exam. You have to show the work, and you have to show me where it came from. So what we're going to do is build a triangle. So just draw any old right triangle. It doesn't have to be in the first quadrant. It can look however you want it to look. And make it, just label the sides so that the arcsine of 1/3 equals y. Right? So that's basically saying sine of y is 1/3, right? Those are equivalent. You're just interchanging x and y. So it doesn't have to be a unit circle. So 3 can be the hypotenuse. It's a lot easier to do the arithmetic if it's not a unit circle. A lot easier. So the problem says we have to find the tangent of this angle, but in order to do tangent is opposite over adjacent. We need to find the length of this side, so compute that next. Just find the length of the missing side and simplify it as much as you can. So this side here is 2 radical 2 because of Pythagorean theorem. Now the tangent of the arc sine is just the tangent of this angle, which is just 1 over 2 radical 2. And then you want to simplify it as much as you can to radical 2 over 2. And that's a decimal 0.707 something, but exact values are required for problems like this on an exam, and the homework as well. So if you need to do a quick review of these topics, go do it. All right, and there's even one more type of problem. What happens if we have cosine of arcsine of x? So this doesn't look like a ratio, right? As I said in previous slides, arcsine's input value should be a fraction. Well, this is really x over 1. So if you see arcsine of x, it's really x over 1. So that means we know two sides of the right triangle. In this case, this is on the unit circle because the hypotenuse is 1. But remember, we're labeling the unknown value as x. We're just labeling the angle as y. Other literature might label that as theta or something. That's fine. I use y just so we can see that it's an inverse function. I just think it's easier. So as we did before, we have to compute the length of the missing side. Again, you will use Pythagorean theorem. So it's just square root of 1 minus x squared. So cosine of that angle, right? So cosine is adjacent over hypotenuse. So it's just radical 1 minus x squared over 1. Simplify it to radical 1 minus x squared. And you might start seeing patterns and similarities, and that's the idea. And that's why I'm not doing any more algebra review of this stuff, right? We're just going to get into the calculus here in a second. But that's what you're responsible for, being able to draw these triangles. Again, for those of you moving on to Calc 2, you're going to draw lots and lots and lots and lots of triangles like this. For those of you who Calc 1 is your last math class, just do your best. All right. So the inverse cosine function has the same domain, right? Negative 1 to 1, but its range is 0 to pi. So you got to remember that. And the idea here is that the ranges are set up so that the function is 1 to 1. Right? If you go back and look at arcsine, those ranges were set up so that it's 1 to 1. This one's set up so that it's 1 to 1. And of course, we have an arctangent function, right, or inverse tangent. Its domain is negative infinity to infinity, and its range is the same as the range of arcsine. So it turns out that this arctangent function pops up absolutely all the time in Calc 2. We're going to do some examples here in a second that use some arctangent. So let's get into some calculus. So here's a limit. So arctan has two asymptotes, two horizontal asymptotes. So you have to know those because these pop up on limit problems. They could be on an exam. And you can just see them from the graph, right? So you don't have to prove these or anything. And if you did need to prove it, you could just say that tangent of y, so y is our angle, has vertical asymptotes at negative pi over 2 and pi over 2. So when you take an inverse, vertical asymptotes turn into horizontal asymptotes, right? So if you needed to prove it, that's how you would do it. So here are our derivatives. I just put them all up there. We're going to look in detail at a couple of these, but I grouped them so that you can see some patterns. Because generally speaking, these are hard to remember. And what we're going to see in the next section adds even more, which makes them even harder to remember. So let's look here at derivative of arcsine and derivative of arccosine. So it turns out the derivative of arcsine is 1 over radical 1 minus x squared. Derivative of arccosine is just the negative of that. right? And derivative of arcsecant, 1 over x times radical x squared minus 1. Derivative of arccosecant is the negative of that. And derivative of arctan, 1 over 1 plus x squared. This is absolutely huge. It comes up monstrously much times, just over and over and over again in Calc 2 and beyond. And the derivative of the arc cotangent is the negative of this. So the idea here is that because of how the arc functions work, these inverse functions, all of the co-derivatives are negative, right? What that means is that you can effectively ignore all the negatives unless you're asked to take a derivative of one of these things. All you have to do is do the derivative of the other one and tack a negative onto it. These don't have special rules. So it turns out that this co-function being negative also works for ordinary derivatives. If you go back and look at section 2.3 or 2.4, oh no, it's 2.4, when we did, derivative of cosine is negative sine, right? Derivative of cotangent is negative cosecant cotangent. So it turns out that co-functions are always negative. So it's a nice rule that always works. So we're going to prove the derivative of arcsine right here. All right, so we're going to say let y be arcsine of x. So that's just coming from our triangle. That means sine of y equals x. So again, we're assuming that domain and range are satisfied. Right? X has to be a number between -1 and 1. It has to be a ratio. Okay, so what we're going to do is we're going to do implicit differentiation on sine y equals x. So that's going to give us cosine y times y prime, chain rule, equals 1, right? So the derivative of x with respect to x is 1. Now what we're going to do is we're going to solve for y prime. It's just 1 over cosine y. Now, we've already said y is arcsine of x. We're going to plug arcsine of x in here. What is cosine of arcsine of x? Well, we proved in an earlier example 1c, we proved that it's 1 over the square, we've proved that this was the square root of 1 minus x squared. So 1 over this is 1 over the square root of 1 minus x squared. And that's the answer. That's the proof. So make sure you guys can prove the formulas for the functions that are not co-functions. So if you were to do cosine, all it does when you take the derivative is it makes it negative. Everything else is exactly the same. So make sure you can do the derivative of arcsecant and arctangent on your own, because those could be on an exam using this method. Practice the method, could pop up on an exam. All right, so there's the proof. So I proved a derivative of arcsine. If you guys wanted to check the other ones, it's real easy to check these. This is not a hard proof whatsoever. So one thing you have to watch out for, just like everything we've seen since section 2.5, is that everything can be combined with the chain rule. So if we're doing the derivative of arctangent of u, it's 1 over 1 plus u squared times the derivative of u. So that makes u substitution problems for integrals really interesting, and we'll get to those here in a sec. So let's do some derivatives just to see how all this stuff works. All right, so the first one we have is y equals 1 over arcsine of x. So what you want to do is you want to write that as, unless you want to use the quotient rule, which I don't recommend, write that as arcsine of x to the -1 power. Now we can just use the power rule when we do the derivative, right? So y prime, bring the power down, lower the power by 1, times the derivative of the inside. This simplifies real nice, right? This is just -1 over arcsine squared. You cannot simplify that as sine to the minus 2. You are not allowed to do that. It has to stay like this. And we know the derivative of arcsine of x, right, because we proved it, is that. And that's actually the answer. And then all I did is simplify it a little bit. I just combined the two denominators together. So, pretty easy stuff. In general, on an exam, stuff from chapter 6 is usually fairly small problems that look like this. Instead of 6, 7, 8 step problems, they're 3, 4, 5 step problems. Other than the things involving logarithmic differentiation, which you guys have seen already. Those get bigger. All right, let's look at the next one. What about the derivative of x times arctan of radical x? So the derivative, this will be product rule, right? So it's first one times the derivative of the second, and the second one times the derivative of the first. However, both, well, we've done this, so I'm using the prime notation here. This one has a chain rule. Okay, so it's x, so the derivative of this is 1 over 1 plus this thing squared times the derivative of this. And then over here, the derivative of x is 1, so I just got rid of it. Don't need it. Now what I'm going to do is simplify this and take that derivative. So this becomes x over 1 plus, well, square root of x squared is x. And then the derivative here, remember this is x to the 1/2, so that's going to be 1/2 x to the minus 1/2. So you can see I'm starting to skip some of the intermediate steps, but you'd still have to show this much work on a test. And then further simplify as much as you can. So if this were a test question, you'd be instructed to simplify. Keep going, keep simplifying, right? So if you want to see where this stuff is going, this 2 got put in the denominator, this x to the minus 1/2 got put in the denominator. And then stuff canceled. X and radical x cancels to radical x, and then I distributed the 2. And the arctan of x just stays, so that's the answer. So you don't have to show work for really basic derivatives, like you don't have to show work for radical x prime. You know that's x to the 1/2, you know how to do that. But anything more complicated than that, chain rule, and when we go backwards and do u substitution, you got to show work for all that stuff. Speaking of integrals, here they are. So all of these integrals follow directly from the derivatives. I proved sine, the arcsine, and I expect you to be able to prove the derivatives of arctan and arcsecant on your own. And then the inverse process, the antiderivative, gives us the indefinite integral. All right, so let's do a couple of these. So I picked 2 arctan integrals here, and then for example 4, I'm going to do an arcsine integral. I just want to show you how u substitution works when you do these sorts of problems. And the hardest one to see how to do it usually is the arctan integral. All right, so the first one is 0 to 1/4, 1 over 1 plus 4x squared. Now, before we go further, look at the formula. The formula says I need to have 1 over 1 plus x squared. This number needs to be a 1. This one doesn't have to be a 1, because whatever this number is, you can pull it to the front. Whatever, if there's a number in front of x, you can factor it out. This is the number you have to make a 1. So when you go look at this is a 1, which is fine. If it wasn't, we could pull it out. This is a 1, which is good, but if it wasn't, we'd have to factor some stuff out. Now, it turns out whatever is here, you just take that number and take the square root and rewrite it like this. And now it's going to be a u substitution. So what we're going to do is we're going to say u is 2x. So that means du is 2dx. And then you have to do that intermediate arithmetic. So we get 1/2 du is dx. So let's make sure we have everything for the substitution. We're going to have 1 over 1 plus u squared. And then dx will be 1/2 du, right? And then don't forget to change the limits of integration to u So u is 2x, so we have to double both of these. So 2 times 0 is 0, 2 times a quarter is a half, but we still have to do it. So I plugged everything in here, 1 over 1 plus u squared, that's u, and then dx is 1/2 du. In the next step, I'm going to simplify all the quantities, and then I should be ready to do an integral. So I pulled the 1/2 to the front, simplified this and simplified this. This is going to be arctan of u, so it's going to be 1/2 arctan of u. I'm going to evaluate that between 0 and 1/2. And I'm going to do this like I've done it before. Factor the 1/2 out, and then solve each of these separately. So arctan of a half is not reducible, so you have to leave it. Arctan of 0 is 0. You do have to simplify this. So if you're doing this sort of thing on a test, I will expect you to simplify arctan of 0 as 0. Arctan of a half cannot be simplified. But arctan of square root of 2 over 2 has to be simplified to pi over 4. So you are responsible for knowing all the arctans, arcsines, and secants for the common angles. Oh, sorry, I said something wrong a second ago. Arctan of 1 is pi over 4. I was thinking arcsine. Arctan of 1 is pi over 4. So if this integral went from 0 to 1, this would be arctan of 1, which would simplify to pi over 4. And your answer would just be pi over 8. So these things simplify a lot or not a lot, depending on what the bounds are on the integrals. But this is the most simplified answer. Do not attempt to simplify it from here. Do not write a decimal. This is what I want to see. So you can see that u substitutions look a little bit different here than they have earlier in the class. Let's do another one. So this is just another kind of tricky thing that you'll see come up from time to time. What happens if you don't have a 1 here? What do we do? Now again, if you don't have a 1 here, you can always just pull that out front. No big deal. But we need to make this a 1. So this is what we do. You factor out the a squared, whatever it is. So again, let's say this number is a 4. Then you'd factor out a 4. If this number is an 8, you factor out an 8. Then what we do is we pull this constant to the front, this 1 over a squared. It's a constant, it comes all the way out. And then the key to the thing is you have to fiddle with this and make it x over a squared. You have to write it this way, or you can't do a u substitution. In other words, this entire quantity has to be squared. Here, it looks low. You might look, oh, that looks fine. I can do that. You have to put all of something, because whatever's on the inside of this parentheses is our u substitution. So that's actually what we're going to do. We're going to say u is x over a. That means du is 1 over a dx. Now, we look over here, we don't have a 1 over a dx, we just have a dx. I pulled this to the front, so we're not including that. It's much easier to multiply than factor, okay? So we're going to say that dx is a du. So when we're ready to do the substitution, we're going to plug in a du here. Right, so I just rewrote that. So this is how it plugs in. So 1 over a squared. 1 over 1 plus, well, there's u, so u squared. Dx is a du. And just like I've done in the past, I'm going to simplify this before I'm ready to do the integral. So this a and this a squared cancel down to 1 over a. You must simplify that. Well, this is just arctan of u. And then you back substitute. U is x over a, so you put it back in. And we're done. So integrals of this type pop up a lot in Calc 2. If you don't need to take Calc 2, well, they're going to pop up a bit in this class. So if you want to use this formula, that's fine. So I proved the formula so you can use it. And that's the answer. So if this number is a 2, so let's say it's 1 over 4 plus x squared, the answer is just 1/2 arctan of x over 2 plus c. You don't have to do all this work again. Right? So that formula is now like an official formula. And it turns out there's official formulas for lots and lots of stuff. We saw some of those when we did logarithms and exponentials. We saw some of those formulas. And here's another one. All right, last example. This is just, I just wanted to show you something other than arcsine. I'm sorry, other than arctangent. This is an arcsine integral. And here's the thing, when you look at it, you might be tempted to say that this is a U substitution. This actually happens a lot. I've had students do this a lot. But the problem is, if you try to do a U substitution, let's say you want to make 1 minus t to the 8th, your U. When you take a du, you're going to get 8t to the 7th du. There's no way to make 8t to the 7th and t cubed compatible. There's no way to do it because you can't take square roots of du. You know what I mean? You can't take roots. You can only do arithmetic, dividing by constants, subtracting, things like that. So you have to take the only other thing it could be. So if this is not a U substitution, well, it will be, but it's not a direct U substitution. What you have to do is you have to fiddle it until it takes the shape of 1 over square root of 1 minus U squared. So here we're going to say U is t to the 4th, so our du is 4t cubed. So by doing this, now we've managed to match up our du, right? So now we have t cubed dt. That'll be 1/4 du, which is not too bad, right? So we just plug everything in. So here I rearranged, just wrote it like this, so it's easy to do the substitution. And here's, 1 over square root of 1 minus t to the 4th squared. Well, t to the 4th is our u. So this does take a little bit of practice. And guys, you're not going to get a ton of practice on the homework. There are some book examples, the homework tutors and that kind of stuff on the final slide here. But some of these can be tricky because you might be tempted to think it's like an ordinary U substitution. But it's not, right? It's a U substitution, and then it's an arcsine integral. So simplify it as you normally would. That's just 1/4 arcsine of U, and then you plug the answer back in. And you can check this easily with a derivative as the other problems, right? So you get 1 over, well, the 1/4 is out front, so we'll just leave it there. So let's just, if you did the derivative of arcsine of t to the 4th, you get 1 over the square root of 1 minus this squared times the derivative of the inside. So that would be 4t cubed, the 4 and the 1/4 cancel, and you get a t cubed. So it checks out. Well, that's it. If you guys have questions, make sure you email me or post on the discussion board. And if you guys need anything else, let me know. And that's it for this video. I'll see you guys next video. Bye-bye now.